Hello, everyone. Uh, Thank you for joining us today. My name is Yogesh Parki. I'm a simulation consultant at Dassault Systems. And today I'm going to talk about accelerating innovation of high-tech devices with ModSim. Here is the agenda of my presentation. First, I'll talk about some of the industry challenges and trends in the high-tech industry, followed by what is SmartSim and how we can use this SmartSim approach in building smart and efficient high-tech devices. So as of today, some of the key business drivers in the high-tech industry are fast-paced innovation, sustainable product design, stringent regulatory compliance, and increasing digital infrastructure. And as a result of these business drivers, there are several challenges and trends we are observing in this industry. First, consumers want reliable devices that they can use day and night with best ergonomics, best camera, and the sophisticated design, but of course at a reasonable price. And this puts a lot of pressure on the device manufacturers because they have to explore and validate multiple designs in a short period of time and launch the product before the competition does. At the same time, governments are constantly enforcing stringent rules and regulations for manufacturers on the topic of sustainability. Just to give you an example, the European Union last year passed a regulation requiring all mobile phones, tablets, and cameras sold in the EU to have the USB-C charging port compatibility. Why? To reduce the electronic waste caused by multiple incompatible chargers. And therefore, Apple, who has these proprietary Lightning connectors, they had to redesign their devices to comply with the regulations. Also, battery life and robustness is another concern. There are several challenges in battery recycling and excessive carbon emissions involved during manufacturing of lithium ion batteries. Therefore, manufacturers are constantly pushing to innovate batteries so that longer the battery life, longer will be the product usage, and we will have less dead batteries ending up in the trash. Now, to understand how unified modeling and simulation or ModSim can help address these challenges, we're going to take a look at the example of BME. BME is a smart projector and a speaker. As it is IoT enabled, it can be connected to the other devices like smartphone, smart TV, or other smart home appliances. And it primarily consists of an acrylic frame, projector unit, electronic speakers, and batteries. Now, some of the key performance requirements for a typical high-tech devices are: first, it has to be smart and connected. So in case of BME, we need to ensure that the Bluetooth antenna is placed at an optimal location for uninterrupted communication. The PCB can transfer high-speed data efficiently, and the device is ready to go through AMI and AMC compliance. Secondly, as you can see here, there are a lot of small components packed in a tight enclosure, so they can heat up pretty quickly. So we have to ensure that the maximum temperature of these components is within the operating limits. This will ensure that the device operates efficiently and does not overheat, ultimately extending its lifespan and the improving overall performance. Third, the device must be robust enough to withstand any accidental drops or unintended abuse scenarios without compromising with its functional or structural integrity. And lastly, the casing is made up of injection molded plastic parts. And we need to identify if there are any potential defects that might occur in the manufacturing process. This will eliminate any expensive and time consuming mold rework later in the production phase. So let's talk about ModSim now. But before that, I just quickly want to talk about 3D Experience Works, which is our on-cloud 3D experience portfolio for SolidWorks customers. Now with 3D Experience Works, you are getting best of both worlds, meaning that you can use SolidWorks for modeling capabilities to design a product. And for advanced multi-physics simulation, you can use the 3D Experience platform to validate the product. And with the 3D Experience platform, it's just not the simulation. The platform is a cloud-based, fully integrated end-to-end solution that brings all the disciplines and stakeholders together. So from design, simulation, all the way to manufacturing, governance, marketing, and sales. And today we are going to focus on the synergy between modeling with SolidWorks and simulation with 3D Experience platform on the cloud. Now, as you can see here, the 3D Experience platform empowers SolidWorks users to run multi-physics simulations on the cloud across different disciplines, such as structures, fluids, electromagnetics, plastics injection, and even rigid body motion. So what is ModSim? Now, traditionally in many companies, design and simulation teams are working in silos, meaning once the design is complete, the designer will throw CAD over the wall to the simulation engineer. And if there is a design change, there is a lot of import and export of CAD data between design and simulation teams. But with ModSim on the 3D Experience platform, we are modeling and simulating in a fully integrated collaborative environment without any loss of data or import or export of various file formats, as in the case of siloed process or the traditional engineering process. So let's see how we can use ModSim to assess the performance of BIMI. And as I mentioned earlier, the key requirements for BIMI are it has to be smart and connected, thermally efficient, robust design, and manufacturable plastic casing. Now, collaboration is a key aspect of the platform. And with the 3D Explains platform, one can collaborate effectively. So as you can see here, we can create communities to share data with internal and external stakeholders. You can track the project status and also update the task that is assigned to you so that you can inform the appropriate stakeholders on the progress of the task. And you can also review the 3D models in a lightweight visualization app without opening the native apps or the rich client. Now let's see how we can assess the multidisciplinary performance of BIMI in the 3D Experience platform. Now the first and foremost step is to save the SolidWorks CAD onto 3D Experience platform. Now in this case here, we have the plugin or the add-in for the SolidWorks user. So within the SolidWorks interface, you can save the model on the platform. And once the model is saved, you can use the appropriate simulation role to set up the simulation. So here we are saving the model and we can quickly check the save status. And once the model is fully saved on the platform, anybody can access this model from anywhere and on any device. And here we are launching the structural model creation app to set up the structural scenario on the platform. So as you can see from the SolidWorks interface, we seamlessly switched onto the platform to set up the structural simulation. So there was no import or export of CAD files or a dump CAD to set up the simulation. Now let's see how we can assess the electromagnetic performance of BIMI. Now, one of the main challenge for electronic devices is that they need reliable connectivity in order to function properly. Without a strong and consistent connection, these devices may not be able to perform their intended task effectively. Now, one effective solution to this problem is that the optimal antenna placement. By placing the antenna at an optimal location, we can ensure that the device has base coverage and the signal strength, and it will provide more stable and reliable connection. Now, in case of BME, the KPIs are the scattering parameter or the S11 parameter should be less than minus 10 decibels, meaning that less than 10% of the signal is reflected and over 90% of the power is radiated or transmitted efficiently. Center frequency should be 2.45 gigahertz. So this is the standard Bluetooth operating frequency. And electrical field blockage should be minimal. So basically minimize any objects or material that could block the antenna's radiation path, as any obstruction cause reflection or absorption, leading to electromagnetic field distortion or localized hotspot, and that may result in failing the EMC emission test. So let's see how the electromagnetics engineer role can enable the optimal antenna placement. So here, the first step, as I mentioned earlier, is to save the model. But before that, we are just inserting the antenna design into our BME model. Since there are different antenna CAD models already saved on the platform, we are just searching in the database and inserting the antenna in our existing CAD. So once we are happy with the antenna location, the next step is we are going to save the model on the platform. So here we have placed the antenna inside the BME. Now the next step is to save the model on the platform. So again, as I mentioned earlier, we are using this 3D experience add-in, which is available for the SolidWorks users to save the model. And once the model is saved, we are launching the electromagnetics engineer role to set up our Emacs simulation. So as you can see, again, I mean, we seamlessly switched from the SolidWorks interface to the CST Studio Suite to set up our Emacs simulation. Now here, once the model is open in the CST Studio Suite, we are going to define the frequency range, boundary conditions, and the excitations. Also, we have the automatic meshing capabilities to mesh the model as well. So here we are defining the time domain simulation, and we define the frequency range and the boundary conditions. Now let's say you run the simulation and if you want to make a design change. Now here what we are doing is we are placing the antenna at a different location, and because we want to analyze the electromagnetic field distribution. Once you update the design, all we have to do in the CST Studio Suite is to check for the CAD update. And once you update the CAD in the CST Studio Suite, uh, all the frequency range, boundary conditions, loading that we have defined earlier will remain as is. We don't have to redefine this or define the scenario setup again. All we have to do is simply rerun the simulation for the new CAD design. So here we ran the simulation for two different antenna locations. And for the new antenna location, the scattering parameter and the center frequencies are meeting the KPIs. And also the modified design has better electromagnetic field distribution as compared to the baseline. Now the manufacturers also need to ensure that the device passes the electromagnetic compliance specified by the regulatory standards. EMC is typically very expensive and time consuming. And with electromagnetic simulations, OEMs can virtually validate if the device is ready to go through EMC and potentially pass the very first time. Now, in our case, we need to ensure that radiated emissions from BME should be within the specified FCC limit. And to measure the signal quality, we will use the eye diagram parameters. So the KPIs here again is that eye height should be greater than 1.32 volts. So higher this number, better is the noise immunity. And eye width should be greater than 0.63 nanoseconds. So this is the time window during which the signal is stable and correctly interpreted as 0 or 1. So we are again going to use the same electromagnetics engineer role to assess the EMC compliance. Now, in the CST Studio Suite, we have something called as the automatic cell lumping technology. What it does is that in the area of interest, it uses a highly refined mesh, and away from the area of interest, it uses the large macro cells and the reduced integration elements to reduce the mesh count. Now, this not only reduces the mesh count, but also reduces the memory requirement without compromising with the simulation accuracy. Now here we are just showing the ease of use of the tool. We are defining the multiple excitations in the one go within a single dialog box. So here we are just selecting the multiple ports. And once we select that, we can apply the excitations in the same user interface. And once the simulation is complete, you can plot the current plot that displays the magnitude and distribution of the surface currents. It is typically plotted at a certain frequency and under a specific excitation. And high current concentration basically helps us identify uh, which radiation sources or what are the radiation sources, which trace or antenna feed line is emitting unwanted EMI. And electromagnetics engineer role has 16 cores of embedded compute, meaning that up to 16 cores, you do not need any license or tokens to run the simulation. And you can run these simulations either locally or on the cloud. In fact, on the cloud, we have the option to run the simulations using CPU or GPU to reduce the simulation turnaround time. Also, we have EMC standard libraries. So here, what we are doing is we are plotting the FCC limit line, and we are making sure that the emissions are within the compliance. So in this case, as you can see, the radiated emissions from BIMI are within the FCC limit. So to summarize, using the electromagnetics engineer role on the 3D Experience platform will enable you to effectively design, analyze, and optimize electromagnetic components and systems. Now, next, let's assess the thermal performance of BIMI. Now, as I mentioned earlier, there are a lot of components packed in a tight enclosure, and they can heat up or they can dissipate the heats when they are powered up. Now, in case of VME, as you can see, we have multiple components that dissipates heat, such as PCBs, batteries, projectors, and many more. So the KPI here is that the maximum temperature should be within the operating limit and minimize any air recirculation inside BME. So now to assess the thermal performance, we are going to use the fluid dynamics engineer role on the platform. Now, one nice feature of the fluid dynamics engineer role is that in order to perform thermal simulation, detailed CAD is not necessary for electronic component models. We can use the abstract models that are available in this role to define the thermal behavior. So here we are defining the heat sink with just couple of inputs. And then we are using something called as the two resistor model to simplify the thermal behavior of a chip. So all we have to define is the two thermal resistances, basically heat flow from the chip core to the case and heat core from the chip core to the board. Then we are using the PCB component model. So we are defining the uh, trace material, substrate material, and the corresponding thicknesses. Again, if you have previously done a similar simulation, then you can simply search for the material in the 3D Experience database, and you can reuse that material for this particular simulation. So as and when you are creating the simulations, when you are creating materials, you are actually creating the material database that anybody can use in the organization to perform simulation. And here again, we are using a thermoelectric cooler component. It's a semiconductor device which, when powered, creates a temperature difference between the opposite sides of the device. And that's why we define the cold side and the hot side. Also, when you're performing fluid simulation on the platform, we do not need of a CAD for the fluid domain. The solver automatically extracts the fluid domain and uses a body fitted boundary layer meshing technique to mesh the air domain. And as you can see here, we have meshed the solid as well as the fluid because this is a conjugate heat transfer simulation where there is a heat transfer between the solid and the surrounding air. And that's why we used hex mesh and the tet mesh to mesh all the electronic components here. Now again, let's say if you want to make a design change, all the design changes, or if you want to modify the geometry, we are going to make that change in SolidWorks. So we are adding a fan next to a chip. So once you make that design change, first step is to save the updated model on the platform. And once the save is successful, all you have to do is go back to your simulation that you have previously set up. So here we are in the 3D Experience platform, and we are simply doing the global refresh to look for any CAD changes. And once you refresh the geometry, it will automatically pick that, okay, there is a design change, and it will insert that the CAD model of a fan. Now all we need to do is define the fan model using these different abstract models that we have in the Fluid Dynamics Engineer role, and simply update the model. It will automatically update the mesh and rerun the simulation to get the new results. And again, the fluid simulation can be compute intensive because of the large mesh count. And in that case, you can use the DS cloud infrastructure, and you can run these simulations all the way up to 144 cores to get quick results. And here we are comparing the results across the different load cases. So we are comparing the results of models with fan and one without fan. We can check the air recirculation areas, so we can plot the velocity streamlines. You can look at the temperature contour plot. You can play the animation. You can create the reports. And here again, I mean, we are just comparing the results side by side between the two designs. And in this case, the one design where we have the fan added, we can see that the maximum temperature is within the operating limits. So in summary, again, using the fluid dynamics engineer role, we can assess the flow and thermal behavior of the product and make more informed engineering decisions. Now next, we are going to see how we can assess the structural integrity on the 3D Experience platform. Now, structural robustness significantly impacts warranty claims and brand image for high-tech devices. In case of BME, the KPIs are: the frame should withstand targeted bending displacement of 5 millimeter, and maximum stress induced should not exceed 150 megapascal. Also, the device should withstand corner and base drops from a height of 1.5 meters. Now, first, we are going to look at the structural designer role available on the platform, which allows us to perform linear structural simulations. Now, one of the nice feature of the platform is that it comes with something called as the assistant panel. So think of this as a like a guided workflow. All you have to do is start from the top, and by the time you reach the end of that assistant panel, you will have simulation ready to run. It basically tells you, okay, what are the steps which are mandatory, which steps are optional, what are some of the key inputs that you are missing for that particular simulation. So this is really useful for the new designers or somebody who is new to the platform. It will help you to set up the simulations quickly. Now, as you may know, simulation on the platform uses the Abacus solver technology behind, and Abacus is widely popular for its nonlinear capabilities. Meaning, if you have a nonlinear material, nonlinear contact, or large deformation, Abacus solver is robust enough to give you a solution. Now, in this case, we are using something called as the general contact. What it does is that it encompasses the entire model. And if you have any surfaces or edge to surface contact that may occur during the simulation, the solver will recognize that contact. So we do not have to explicitly define each and every contact pair in this case. With just one contact pair, the solver will take care of the contacts that may occur during the simulation. And again, if you want to do any quick design exploration, let's say you want to run a simulation by changing the material, you can again look up for the new material in the database and you can overwrite the previous material. And when you are running the new simulation, you have the option to either overwrite the results or keep the previous results. So if we keep the previous results when running a simulation, you can compare the results between the old design and the new design. So here we ran the simulation with two different materials. And as you can see with the new material, it is meeting the KPIs where the maximum stresses are less than 150 megapascal. Now next, we are going to use the structural mechanics engineer role. Now here we are using a different role to set up the non-linear explicit impact simulation. Now structural mechanics engineer role, you can think of this as Abacus on the platform. It has all the Abacus capabilities and functionalities. So if you want to perform, let's say, non-linear i- structural implicit or explicit simulations, you can use structural mechanics engineer role. And it comes with 8 cores of embedded compute. So again, if you want to run simulation locally or on the cloud up to 8 cores, you do not need any licenses or tokens to run the simulation. So here, as we discussed earlier, we are going to perform corner drop as well as the base drop. In both the cases, the only difference is the orientation of BME. So rather than creating the drop case for a different scenario, what we are doing is that we are simply duplicating the mesh. And when we duplicate the mesh, all the properties, group definitions, abstractions get automatically duplicated. So in the duplicated case, all we have to do is either change the orientation of BME or change the ground orientation and just run the simulation again. And same goes with the analysis case. Since we have already created the drop case for a corner drop, we are duplicating the analysis case. So when we duplicate the analysis case, again, all the initial conditions, interactions, boundary conditions, loads, if you have defined any specific output request, they all get duplicated. So we don't have to recreate the analysis case again. And here, as I mentioned earlier, we are using Abacus explicit dynamic solver to set up the simulation. So here we are defining the impact duration. Then we are going to define the initial velocity. So depending on the drop height, the initial impact velocity is going to change. So here we are defining the velocity in the negative y direction. Then the next step is the contact. So we can use the general contact definition and we can define the friction properties. Again, we have the flexibility to define like a specific contact pair friction properties also. So if you want to define a different contact friction coefficient for another contact pair, you can do that. And then here we are fixing the ground. Since the ground is modeled as a rigid body, we are selecting the reference point of that rigid body and we are fixing it in all the 6 degrees of freedom. And lastly, we are just defining the gravity in the negative y direction. And with that, we have set up, we have defined the scenario and we can run this simulation locally or on the cloud. So as I mentioned earlier, again, structural or fluid simulations can be very compute intensive. Structural simulation, if it is highly nonlinear, where you have, let's say, a continuous change in contact or large deformation, they can be highly nonlinear and can take long time to run. So here again, we can run these simulations on the cloud. As far as structural simulation goes, we can run the simulations on the cloud all the way up to 192 cores. And we have the flexibility to run the simulations sequentially or concurrently. When you run the simulations concurrently, the second simulation will require tokens. But let's say if you decide to run the corner drop and the base drop load cases sequentially, up to 8 cores, you do not need any tokens to run this simulation sequentially. So as you can see here, for our SolidWorks users, we have these two different roles available on the platform to perform structural simulations. If you are interested only in linear static simulations, you can use structural designer role. But if you want to use highly nonlinear implicit or explicit simulations, you can use the structural mechanics engineer role on the platform. Now, lastly, we are going to assess the manufacturability of the product. Now, by simulating the injection molding process, designers can identify potential issues early on and can make informed decisions to ensure manufacturability and prevent any expensive and time consuming mold rework downstream. So by simulating the manufacturing process, we can look at these different defects such as sink marks, weld lines, air trap, etc. So here we have simulated the molding process and we are looking at the fill time. So this is nothing but the time required to fill the mold cavity. We can also look at something called as the ease of fill. Now it displays the relative pressure required to fill each region of the cavity. For example, here the green region can be filled with pressure below 80% of the maximum injection pressure. Yellow region is where it requires a slightly higher injection pressure. And the red region is where it requires pressure that exceeds 90% of the maximum injection pressure. So in this case, all these protrusions here at the center, you can see that we require maximum injection pressure to fill that cavity. We can also analyze sink marks, which are nothing but the defects that occur because of the shrinkage of the material and it appear as a shallow depression or dimple on the surface of the part. Now the solver analyzes the geometric features that are likely to induce sink marks, such as ribs, bosses, gussets, and fillets. And it also calculates the location and the depth of the sink marks. We can also visualize the weld lines, which typically occur when the flow front meets during the filling process, and this can potentially form a weld line defect. Now, the mold designer or the part designer, they have to ensure that there are no weld lines near the structurally critical or weak areas of the plastic part. In that case, they might have to add more gates or increase the injection pressure uh, to see if that changes the results or not. We can also look at the air pockets that may develop during the filling process. And in that case, we might require the addition of the vents to get rid of the air pockets. So by simulating this injection molding process, we can visually check for the air traps to prevent defects or imperfection that may lead to structural or functional failures. And lastly, we can also simulate the warping. So typically after molding process, there might be some residual stresses in the part. And when we take the part out of the mold, because of these residual stresses, there could be warpage in the part. And the mold design engineer has to make sure that the warpage is within the tolerance and is not significant enough to cause any assembly defects. Now, in order to simulate this warping, again, we can use the Abacus solver uh, to kind of calculate this warping. So with the plastic injection engineer role, the part designers as well as the mold tooling engineers can validate and optimize injection molded part designs. So as you can see here, within this single user interface, we were able to assess the multidisciplinary performance of BIMI. So what are some of the benefits of modeling with SolidWorks and simulating with 3D Experience platform? First of all, the platform is fully integrated with SolidWorks. Apart from unified modeling and simulation, the platform provides digital continuity across the product lifecycle, starting from the requirements. Also, the platform is very design centric. As we saw, we have this assistant panel, which allows designers or non-expert simulation users to set up the simulation effectively on the platform, and it reduces your learning curve drastically. Also, we have multidisciplinary capabilities available within the single user interface. So whether you want to perform structures, fluids, EMAG, motion, or plastics, we have all the capabilities available on the 3D Experience platform, which are fully integrated with SolidWorks. Also, some of these simulations, such as fluids, structures, or even EMAG, they can be very compute intensive. And even if you don't have local infrastructure to run the simulation, you can always leverage the DS Cloud infrastructure to run the simulations all the way up to 192 cores to reduce the simulation turnaround time. Also, the platform is scalable, meaning that based on your user skills, product size and complexity, and development stage, you can pick and choose the different roles that would meet your requirements. And as you expand your portfolio, or as you expand your offering, you can select more advanced roles, or you can increase the number of roles to meet your analysis requirements. And lastly, the data is securely saved on the cloud that allows collaboration within and outside the organization seamless and effective. So how does this help businesses? By modeling with SolidWorks and simulation with the platform, you can explore multiple design alternatives quickly, which will accelerate your time to market. The multidisciplinary capabilities available on the platform enable you to innovate broader product portfolio. By evaluating the product early in the design stage, uh, the company can reduce the prototyping, compliance, and warranty cost. The platform will enable you to enhance the communication and operational efficiency. And by leveraging the cloud infrastructure, you can overcome any hardware barriers. So this is how the platform will help you to stay ahead of the competition.